Okay, guys, we are on to packet number 5, Introduction to Logarithms. And the first lab is the first 4 pages of your packet. And we're going to start the intro to logarithms. Okay, so first of all, I want to introduce logarithms as the inverse functions to exponentials. Okay, so these are inverses to exponential functions. Inverses of exponential functions. All right, and you really probably don't have much exposure to inverses. So I'm going to kind of give you a couple of facts about inverses. We'll write it up here. Okay, so to get an inverse of a function, you basically, the x and the y are switched. Okay, so the xy, all xy pairs, for instance, of an exponential, will turn into, okay, we're just switching them around. The y becomes the x, so the y is first and the x is second. We just switch the x and y around, okay? And so since we're switching the x and y around, we can also see the graph of this, okay? It's a reflection. Inverses are reflections in the line y equals x. Okay, so that's what we're going to explore on this page. All right, and if you look at the notes here, this line, do you see how it's 0, 0, 1, 1, 2, 2, 3, 3, 4, 4? This is called the line y equals x because every x and y pair match on this line, right? 5, 5, 6, 6, 7, 7. Y is equal to the x value. And just to give it a little bit more knowledge of inverses, I'm going to show you a Desmos thing I came across. Okay, and this is basically the exponential function, okay? The exponential function where a base is 2. Okay, and I've actually, you can see the coordinates if I click on these. And if the base is 2, that means for every x value that goes up by 1, the y value is multiplying by 2. So 1 times 2 is 2. This is going to be 2, 4. 2 times 2 is 4. This will be 3, 8. Okay, so I can see the growth factor by looking at what the y value is multiplied by for every change in x. Okay, this is an exponential. Okay, so I'm going to show you, okay, let me move I'm going to show you the graph of y equals x. Okay, this is, my scale is off, so it doesn't really look like the 45-degree angle that it should. If I do this, it'll make it look, okay, now the x and y scales are a little closer. So this is my exponential, and if I click up here, it'll graph the log with the same base. Okay, so this is the log, and you can tell if this is the line y equals x. If I reflect it, this is the log graph. Okay, it's the mirror image of this exponential and the line y equals x. Okay, so if I look at the actual coordinates, okay, you'll see the coordinate, remember, of this exponential is 1, 2. Its reflection is just 2, 1. Okay, if I want some more, I can just push enter, I realize, and I can get more points. On my table over here, under the settings, you can click table. So again, if I look at this point, its reflection will be the reverse. Do you see what I mean? The x and y are just switched. Okay, so that's how you get an inverse of something. You basically switch the x and y values, you plot the points, and if you're doing it correctly, it should be a reflection in the line y equals x. Okay, and inverses of any function are defined that way. Reflection in the line y equals x, and we switch x and y. Okay, so that's just a introduction to inverses. Okay, so basically that's what we're going to do. Okay, they have, we have the exponential function shown here, basically y equals 2x, right? And just to reiterate, right, this is in the form y equals a b to the x. It's just function notation. So the a value, since there's nothing there, there's nothing written there, the a value is 1, so the y intercept is 0, 1, and the growth factor is 2 here. Okay, the growth factor, or we're going to start calling this the base. Okay, the base of the exponent, the base or the growth factor is 2. Okay, and again, we can see that because we can see the growth factor as the x values go up by 1. We can see this is a times 2 pattern. Okay, and it's more evident with the whole numbers. We're more familiar with that. Okay, so we're skipping the one-to-one functions. We haven't talked about that yet this year. But what we're going to do is we're going to plot the inverse. Now, this, if we have a function, any function f of x, the way we notate the inverse, okay, this is not really a -1 power in this case, since it's saying that the inverse of function f. This is what this means. Inverse of f of x. Okay, I know it looks like a -1 exponent, but if it's between the f and the x, it indicates the inverse of f of x. So that's what that notation means. Okay, so here they want us to create a table for the inverse of f of x. So like I said, we're just going to switch the x and y. So our x's in this exponential are -3 to 3. Okay, that's our x's, or our domain for this one is -3 to 3. Well, if I switch the x and y's, that domain of this function is going to become the range, which is the range of just all the y values of its inverse. Okay, we're switching the x and the y's. Okay, so the domain of one becomes the range of the other, and the range of the original, okay, the range is just all of the y values, that becomes the domain of its inverse. And again, I'm just simply switching the position of the x's and the y's. Okay, so, and we'll talk about this later. So since this is an exponential and this is the inverse, this is actually a logarithm. That's what a logarithm is. Okay, it's the inverse of an exponential. So if I'm going to plot these points, okay, I'm going to plot the points found on this table below, 1/8, -3. Okay, so 1/8 is going to be really close to the y-axis, -3, which is the reflection of this point. The next one was 1/4, -2. Again, really close. 1/2, -1. All right, and then I have the point 1, 0. Okay, and then 2, 1. Okay, then 4, 2, and 8, 3. So 8, 3. Okay, so this is my first logarithm. Okay, this is, and like I said, if this is f of x, if I can notate this as f of x, I can also just say this is the inverse. Okay, so this, we just did an inverse graphically. So it says, what would be the first step to find an equation for this algebraically, for the inverse of this algebraically? Write the step down and then stop. Okay, so our original function, okay, instead of saying f of x equals, instead of doing this, f of x equals 2 to the x, that's the same as, right? I can write it as y equals 2 to the x. So algebraically, I just have to switch the x and the y. All right, so algebraically, the inverse of the function, instead of y equals 2x, it's going to be x equals 2y. All right, so this is the inverse. Now, in order to solve for y, to solve for an exponent, okay, we usually like our equations in y equals form, right? So to write this inverse solving for y, that's when we're going to have to change it into log form. Okay, any exponential can be changed into log form. So this is on the next page, we're going to be changing our exponential of y equals 2x into log form. Okay. Okay, so I'm going to kind of, first of all, this is where they introduce, it says defining logarithmic functions, the function, and then it has this. I'm just going to write how you should say that, okay? So basically you'd say y is equal to, that's the easy part, right? We read this as log, oops, there's no E on log, I don't know why I wrote that. Log base B. Okay, this down here is the base. In this case, it's log base B of x. That's how you read it, okay? So y is equal to log base B of x, okay? And this is the inverse of this function y equals b to the x, okay? And here, so since this is the inverse of this, okay? Remember I said for inverse, we switch the x and y. The inverse of this can also be written as x equals b to the y. That's the inverse of this. The inverse of this, we switch the x and y. Therefore, y equals log base b is the same thing as b to the y power equals x, or x equals b to the y power. Okay, so logs can be written in exponential form, and exponents can be written in log form. Okay, so notice in both of these, the base stays b. Okay, in both of these, when you're converting from one to the other, the base stays the same. They're in different locations for a log. The log base is down here, and the base of an exponent, okay, we should know, familiar where the base of an exponent is. So the base stays the same. All right, now what we're basically doing is the input and output switch, okay? So we switch the input and output. The input and output switch. So for a log, okay, whatever it's equaling is the output. So y here is the output. Well, x is the input. Okay, if we're converting it to an exponential, okay, now y is the input and x is the output or the result. Output is the same thing as the result, the thing that's by itself in the equation. Okay, so that's like a very brief. We'll practice this. Okay, so here we see, okay, this is our exponential, obviously. This is an exponential. Okay, because we have an exponent. Okay, and our base 2, okay, our base is 2. Our exponent is 3. And that's our input. And our output, or our results, equals 8. Okay, so if we switch that over to a log, okay, if we're converting it to a log, which this is a log, or a logarithm, short for log, you could just put log, but logarithm. Notice how our base is still 2, and they have it color coded here. The base is 2, but now our input is the 8, and the output is the 3. Okay, so the output of a log was originally the exponent of the exponential. Okay. Okay, so it takes a while to get used to these logs. Okay, but we're going to start evaluating them. All right, so basically, when we're finding the result of a log, this result represents an exponent of an exponential. the exponent of the exponential. So basically we're asking ourselves, is the base 2, so we're going to say the base of 2 is raised to what power to equal 8. Okay, that's what we're thinking when we're doing log base 2 of 8. Okay, so we're thinking, okay, 2 raised to what power equals 8? And hopefully we know that 2 to the third power is 8, so the answer to this is 3. Okay, that's what a log is. We're just, in order to solve, we're writing it like that, 2 to what power equals 8. Okay, so in this case, we're saying our base 4 is raised to what power to equal 16. So if we wanted to write this as an exponent, an exponential, I'm going to put an unknown of x here, and I can rewrite it. Okay, the base stays the same. The output, in this case, which is x, becomes the input, and my input of 16 becomes the output. All right, so I'm asking myself basically 4 to what power is 16? So this would be x equals 2. 4 squared is 16. Okay, so maybe you can pause the video and try a couple of these on your own, but I'll go through all of these with you just because it takes some time to get used to. Okay. All right, so we're saying the base 5, because the base always stays the same. The base, this output becomes our input for the exponential, and the input becomes our output. So we're saying what power of 5 becomes 625, okay? And you may or may not know this, okay? So you might have to play around with it a little bit. But I know that 5 squared is 25, and I know that 25 times 25 is 625. So I know that 5 to the 4th is 625. So x equals 4. Okay, and you can also use your common base paper to help you with this. Okay, we have all of the powers of 5 that are greater than 1 for a bit on that paper, so you can look at that. Okay, now log base 10 is actually a special, this is called the common log, which we'll talk about later. But if it has a base 10, we call it a common log. I'm just going to intro that now. We're not going to talk too much about it, but we're still doing it the same way. This is 10 to what power equals 100,000. And with tens, it's kind of easy because 10 to the first power, if it has 10 to the first power is just 10. 10 to the second power is 100, third, fourth, fifth. So basically you just count the number of zeros if you're finding what power of 10 it is. So this is x equals 5. 10 to the fifth power is that. All right, and then we'll practice with some of our negative and fractional exponents. Okay, so basically this is saying, okay, 6 to what power equals 1 over 36? And hopefully you know that 36 is 1 over 6 squared. So we have to know that x is negative 2. Okay, 6 to the negative 2 power is 136. All right, so 2 to the what power is 1/16? Well, I know 2 to the 4th power is 16, so x must equal negative 4. All right, another way of writing log 5 to the square root of 5, well, the square root of 5 is 5 to the 1/2 power. And if you write it like this, it makes it super easy because basically you're saying 5 to what power is 5 to the 1/2 power. Okay, so x would have to equal 1/2 here. Okay, or maybe you didn't even have to do that. Like, you know that radical 5 is 5 to the 1/2 power. So you could have just jumped to that. All right, last one to practice. And again, you might want to rewrite this. 3 to the x power equals the 5th root of 9. Okay, maybe you want to rewrite it as 3 to the x power equals the 5th root of 3 squared. We can change this into a fractional exponent, right? The power is 2, the root is 5. So 3 to the x equals 3 to the 2/5, therefore x equals 2 to the 5th. If you have an Inspire or if you Google log calculator, you'll be able to change this base. But for Desmos on the scientific calculator, you cannot change the base. So these we would have to all do using our knowledge of exponents. All right. It's critically important to understand that logs give exponents as their outputs. Okay, everything we just solved for, right? This 3 represented an exponent of an exponential. This 2 represented the exponent of the exponential. If I wanted to kind of check this, okay, I'm going to just check part B here. I could say, okay, my base for this answer to the log is actually my exponent to my exponential, and then the input of the log is the output of my exponential. So 4 squared equals 16, it's a check. Okay, so they're inverses because the inputs and outputs switch, or the domain and range switch. Okay, and we need to have an understanding of that. Okay, so I'm just going to write a little blurb here. Does it let me insert a text box? Into text. Okay, I'll just write it. I'll try to do my best to write neatly. Okay, so the output or the answer to a logarithmic function the answer to a log is an exponent. Okay, the output or answer to a log function is an exponent. Okay, an exponent it's an output of a logarithmic function, but an exponent is an input for an exponential function. Okay, remember, the base remains the same. You just switch inputs and outputs. Remains the same. The base remains the same. The base remains the same. So if you are asking about log 2 of 8, okay, the base 2, the base, which is 2, okay, this is what they're asking. The base 2 must be raised to what power? To equal 8. That's all it's asking. So we need to get used to seeing this as 2 needs to be raised to what power in order to give you the answer or output of 8. It's basically what we're doing. We need to get used to that. All right. The next page, the next page is the last page of notes, and these problems look a little bit different. It throws in some other stuff that we've learned and mixes in some other stuff with logs. Okay, so it gives us this log function. Okay, it looks a little bit more complicated. Which of the following would represent its y-intercept? Well, again, I've mentioned this before. Once you hear y-intercept, you should think, oh, x equals 0. All right, and that will allow us to solve for y. So y equals log base 2 of 0 plus 8 plus 9. Okay, well, that's the same as y equals log base 2 of 8 plus 9. All right, so now if we see log base 2, we can actually evaluate that, right? Since 8 is a power of 2, we just talked about this on the last page, this is basically saying 2 to the what power is 8. So log base 2 of 8 is just 3, because 2 to the third power gives us this 8. So this becomes 3 plus 9, and the y-intercept would be 12. Now, if if you're totally confused by this, we could do it graphically, because on Desmos, it does allow you to change the base. So let me just show you that. Okay, if I'm going to go just to a regular Desmos graphing, I can type in y equals, all right, and I wanted to show you this. You have to go to the functions down here, functions, and oh, it's under miscellaneous functions, and you'll see log and base A here. Okay, log base A allows you to put any base there, so log base 2, and then I'm going to type in x plus 8. I'm going to close parentheses, and I'm going to put plus 9, okay? And I could actually, it shows me the graph, and I can just click on that point, and it gives me the y-intercept of 12. So that's the other way to do it. Functions miscellaneous will give you the ability to change the base for the log. All right, next one. There's one like this on your homework, I believe. Between what two consecutive integers must log 3 of 40 lie? So basically they're saying 3 to what power equals 40? Well, we know some powers of 3. I know 3 to the third is 27. Again, you can use your common base sheet. And 3 to the fourth is 81. So since 40 fits between there, the exponents must be somewhere between 3 and 4. That's it. Okay, so remember, you need to think about what this is asking you. 3 to what power equals 40? You can change it to an exponential and then think about it from there. All right, so it says most calculators only have 2 logarithms, okay? One of them is log 10, base 10 of x, and it's called the common log. And normally you'll see it without the base 10. So if you just see log of x, the implied base is 10, okay? So this says evaluate each using your calculator. So if you do use Desmos, the scientific calculator, it does allow you to just use either the log or the natural log. Okay, so if you go again to functions, you'll notice it's only the choice of log and this ln, which is natural log, which we'll talk about later. So the only scientific, the only log on Desmos that it lets you use is a common log, and the log of 100 is 2. Okay, and this should make sense to you, because if we actually put the 10 in there, basically what this is asking is 10 to what power equals 100? So that's a 2. All right, so we really don't need our calculator, but you can use a calculator for these. Again, this, if you don't see a base, it means it's a base 10. So I know 10 to the third is 1,000. So 10 to the negative third must be, give me the fraction of 1/1000. All right, again, here I can write this. This is just means log base 10. The square root of 10 is 10 to the 1/2 power. So 10 to the 1/2 power obviously is 10 to the 1/2. All right, next one. Can the value of log base 2 of -4 be found? Or what about log base 2 of 0? Why or why not? Okay, so if I want to write this as an exponential, I would say 2 to the what power equals -4. Well, you should know that 2 to no power gives us -4. This is not possible. Okay, so no exponent, 2 raised to no exponent is going to give you -4. Okay, this is impossible. So this is impossible. Okay, it also asks about log 2 of 0. Okay, so basically this asks, okay, 2 to what power equals 0? Well, exponentials, hopefully you're thinking exponentials, there's an asymptote at y equals 0. This cannot happen either. Okay, so when we have exponentials, remember, there's an asymptote at y equals 0. We can never equal the value itself. 2 raised to any power never equals 0. It's always greater than 0. Okay, so since the range of exponentials, what's true is y has to be greater than 0. Okay, it can't equal 0. It has to be a positive value. So since logs are the inverse, that means the domain of logs must be positive. So x has to be greater than 0, okay? If the range of exponentials becomes the domain of a log, and therefore the domain or the x value, the input must be greater than 0. Okay, so your homework is to do questions 1, 2. Remember to show work, either graphically or algebraically, whatever you feel more comfortable with, but show work. If you're going to graph, show a sketch. Number 4. For number 5, I'm crossing out C and D, okay? But you can do A and B. You should be able to do those easily, hopefully. And then for number 6, I'm going to cross out number D. So your homework is just to finish page 4. Okay, have fun with it.